Greetings from Istanbul Technical University. I am Batuhan, the team captain of IT Rover Team. We are proud to announce our 9th generation rover, ARC' Rover, as we are prepared for Anatolian Rover Challenge 2025. Established in 2016, the IT Rover Team focused on space robotics with a specialization in rover science. Since our establishment, we have been pioneers in this field by advising and supporting other organizations interested in space robotics, striving to lead and represent Turkey in international competitions. As the only Turkish team that has brought multiple international awards to our country, we compete in the Universal Rover Challenge, European Rover Challenge and Anatolian Rover Challenge. In 2018, we won the Best Science Systems Award at the Universal Rover Challenge and have since earned accolades for Best Maintenance Test, Best Presentation Test, 3rd place and 2nd place in the European Rover Challenge over the past 4 years. Now, we are excited to set new milestones at Anatolian Rover Challenge 2025.
The IT Rover team is structured with a clear hierarchy led by a team captain who coordinates 5 specialized sub-teams: mechanical, science, electroware, organization and design. This setup ensures that a wide variety of expertise is brought into the decision-making process, significantly enhancing the project's overall success. To streamline our workflow, we rely on Asana for planning timelines and Trello for assigning tasks. These platforms help us clearly visualize our responsibilities and deadlines, making it easier to track progress and adjust quickly to any project requirements. When it comes to designing, constructing, and testing the rover, we follow a meticulous and hands-on approach. We utilize our campus facilities to assemble the rover and conduct extensive testing, replicating, and conditions we expect to face during the competition. This rigorous testing phase not only confirms that the rover functions as intended in the theory, but also ensures it's practically in real-world scenarios. By doing so, we can identify and address potential issues on the spot, ensuring the rover is both reliable and ready for the competition.
Crafted with both form and functionality in mind, the rover's robot chassis is designed for exceptional durability. It's constructed from T-slot aluminum tubes that offer versatile modularity. Its chassis is divided into 2 integral components, a sturdy frame and a central column, which together form the foundation of its design. To ensure optimal stability on varied terrain, the rover is equipped with rocker suspension system that incorporates a differential bar, effectively balancing its weight distribution. The movement is driven by brushless DC motors, ingeniously hosted within aluminum hubs to protect them from external factors. Enhancing its performance further, the wheel rims are made of ABS while the tires are manufactured from TPU. In terms of dimensions, the rover measures 1.1 meters in length, has an overall width of 1 meter including the wheels, and maintains a ground clearance from 0.3 meters.
Our rover is designed to be powerful, efficient and reliable. At its core, a 42-volt lithium-ion battery provides the necessary energy for all systems. Our custom power distribution board regulates this power, ensuring stable voltage levels for each component. We have integrated an emergency button in an easily accessible location. With a single press, the battery disconnects, immediately shutting down the entire system if needed. The driving system is managed by ARM-based microcontrollers on our custom vehicle control unit. This unit not only controls movement but also manages the rover status LED, providing real-time visual feedback. For precise and smooth motion, we use PID-controlled brushless motor drivers to operate our BLDC motors. These motor drivers communicate with the VCU over the CAN bus protocol. Hall sensors ensure stable motor performance with router position data, while encoders enable precise closed-loop control for complex terrain.
Our vehicle control unit includes various types of microcontroller, each chosen to meet specific requirements. We prioritize the security and resilience of all communication protocols on the rover. Therefore, communication between the rover computer and microcontroller systems in the vehicle is based on reliable protocols, such as CAN bus, which are used for communication between the BLDC motor drivers and the vehicle controller unit. Also, VCU is connected to the local area network of rover via TCP or UDP protocols. In main computer, we use ROS to simplify communication. It provides a flexible framework with a publish-subscribe model, making it easy to manage communication between distributed systems.
In our 6 degree of freedom robotic arm, we use a custom-designed cycloidal reducer that we developed ourselves. Cycloidal reducers provide high torque transmission while maintaining low backlash, ensuring precise and smooth motion. This allows our robotic arm to operate with stability and minimal vibrations, which is crucial for tasks requiring accuracy in challenging terrain conditions. In addition, we use carbon fiber tubes and aluminum to make our robotic arm both lightweight and durable. This reduces the overall weight, improving agility and efficiency. Our robotic arm is capable of handling a variety of tasks.
The encoder data was used as position feedback in the PID control loop to provide precise control of the robotic arm. Communication with the motor drivers was established via the KNFD bus. ROS was used to process sensor data and transmit calculation results to MOVELT. MOVELT uses inverse kinematics to determine joint movements, allowing the arm to open and close switches, press buttons, open drawers, and type on the keyboard. The manipulator was tested for optimal functionality in simulation systems like Gazebo. A USB camera was also integrated to improve the gripper's performance.
The rover utilized 5.8 GHz module for communication with the state machine. Localization is provided by the SLAM algorithm, which uses RTK GNSS and our customized GNSS model in combination with the IMU and LiDAR data. Localization is used for path planning and obstacle avoidance. LiDAR sensor generates point cloud data for obstacle avoidance and creating a cost map. Depth camera are used for our custom artificial intelligence and algorithms that we use in search missions. Rover uses a spiral search algorithm to detect ARC attacks from long range. The rover can also be controlled manually via state machine. In addition, the state machine allows to visualize rover status such as battery, speed, localization, etc., as well as visualize scientific graphs.
For the ARC competition, we developed a core drilling system that serves both as a sampling system and storage unit. The drill bit reached depths of up to 20 centimeters, successfully collecting 5 grams of soil as required by the competition. Once the collection process is complete, a spring-loaded mechanism activates, rotating the cover by 180 degrees to seal the chamber and protect the samples from external factors. This ensures the samples remain secure and uncontaminated for further analysis. Designed with lightweight and durable materials, the system maximizes efficiency in harsh terrain and integrates seamlessly with the rover. Its practical design guarantees reliability and robustness during field operations. The system is 20 by 30 by 70 centimeters in size and weighs 8 kilos.
As a science subteam, we aim to detect phospholipid, amino acid, ATP, aldehyde, and glucose in our soil sample. Since living organisms require a close structure to maintain internal entropy to prevent degradation, we developed a polymerized QCM surface capable of detecting phospholipids, the key components of cell membranes. To identify aldehydes and amino groups, we applied the mean hydrogen test and shift region, enabling amino acid detection in the sample. Our carbon dot-based region detects ATP molecules. For glucose, we use an enzyme-based calorimetric biosensor on Wattman paper, analyzed via RGB imaging. Additionally, our UV spectrometer measures the concentration of these biochemical tests. We also employ atmospheric and subsoil sensors to analyze environmental conditions, measuring parameters such as temperature, pressure, humidity, pH, soil moisture, and ionic compositions such as nitrogen, phosphorus, and potassium. Gas sensors monitor carbon dioxide, methane, ammonia, and nitrogen release, with detection and ratio analysis serving as key indicators of metabolic activity. These gas measurements are conducted in airtight containers for accuracy.
We use a 785 nanometer Raman spectrometer with a diode laser to minimize fluorescence from organic molecules and detect biosignatures supporting our habitability hypothesis. Raman scattering analysis reveals mineralogical properties based on chemical bound vibrations. A depth camera scales stratigraphic image, while a high-resolution camera helps in identifying and interpreting rock texture. Literature suggests that the solid plenum region's lava plains are Noachian and Hesperian in age. Graben structures, faults, especially listric faults, indicate significant deformation. Various wrinkled structures provide insights into paleostress and thermal evolution. Ejected deposits, veneer structures, and lobate flows further indicate intense volcanic activity.
Our user-centered interface facilitates command execution, video feed display, and scientific graph visualization. Robot Operating Systems framework is used to gain effective control of the rover. 5.8 GHz communication modules are employed for communicating with the ground station. For long-range tasks, we rely on 2.4 GHz RF and 900 MHz LoRa modules. While the 2.4 GHz module handles high-bandwidth tasks like video streaming, the 900 MHz module manages the telemetry data. All our cameras are encoded in H.265 format to minimize data size, ensuring efficient transmission even in poor radio conditions. We are able to visualize both the map and the rover's current position within our user interface with the data.